Uh, Hello again, everyone. Sorry, I'm a teensy bit late. Had a few technical difficulties. Zoom is not cooperating for a second. Can everyone hear me?
Yeah.
Cool. Sounds good. All right. Okay. A few announcements. So I just got like 50 emails yesterday. All of those were your scanned exams. So that's how we're going to be returning those to you guys. So I'll be tallying up the scores today and sending those out to you guys individually. So yeah, I should have the scores input sometime today, and yeah, I'll send them back, scans of those to you guys, because none of us are really expecting to return to school this semester. Make it easy and put all hundreds in. Sorry, don't think that's going to happen, but you will get them back. Average, I'm not sure. I haven't tallied the scores yet, so I actually have no clue. What are you doing? I have no clue what the grades look like yet. So I know as much as you do now. Well, okay, I've graded one problem, but that's all I know so far. Also, yeah, so I'm doing the physical whiteboard. Oh, can you see our dog, my dogs? If they want to come in. They'll probably come in later. Maybe I'll have a doggy stream or something once I figure this out. School switching to pass-fail. I'm not sure. I've definitely heard people arguing that we should switch to pass-fail, and I'm not sure whether or not that's going to happen. So I can't say for sure about that yet. Also, man, okay. What else? Oh yeah. So I'll be next time. I haven't gotten a stylus yet because I haven't really been out of the house much. But I plan on getting one, and I'll probably be doing the virtual whiteboard to do lecture, which will be much easier because I don't have to erase anything. It'll probably be easier to see, and yeah, it'll be nicer. Anything else? Don't remember. When I remember stuff, I'll make announcements. I'm sorry. I'm a bit out of it right now. Okay. Anyways, so continuing what we talked about last time. But yeah, any other questions? Awesome. Let's see what participation is like today. How many people do we have? Sorry, just a sec. Can anyone see how many people we have here? For some reason, I don't know. Can't find that for some reason. 34. Not fantastic, but I guess that'll do. Okay. All right. So yesterday we started talking about limits of functions of two variables. And we saw that the situation was a lot more complicated than for functions of one variable. In fact, really, we just showed how to show limits don't exist yesterday. So remember, if we want to, let me say this one. So if we have a function of two variables, f of x, y, if we want to show that the limit as we approach the point A, B of our function of two variables if we want to show that it does not exist, what we need to do is we just need to find two paths approaching AB so two paths approaching our point, which when we take the limit along those paths, we get different answers. We get different limits along both paths. So two paths approaching AB, along which we get different limits. So we get different limits. So if any two paths have different limits along them, the limit does not exist for our function at that point. In order to show that the limit does exist, I sort of implied that we have to check every possible path, which is not feasible at all. So it might seem really hopeless that there's really no hope of actually showing the limit exists or calculating the limit, but that's not entirely true. We're going to look today at how we do that, and it turns out there's going to be a nice shortcut, and that shortcut will be continuity. Okay, so continuity to the rescue. Okay, so the definition for continuity for functions of two variables is the same as for functions of one variable. So a function of two variables, f, so f of x, y, we say it's continuous at the point AB. Can everyone read this? Looks reasonable, I guess. Okay. So we say a function is continuous at the point AB if the following two things are true. If the limit as we approach AB exists, so limit as we approach AB of our function f exists. So in order to be continuous at AB, the limit first of all has to exist. And secondly, whatever that limit is has to just equal to the value of the function at AB. Let me put it this way. So if the limit exists and that limit is equal to f evaluated at AB. So the limit exists at the point AB, and that limit is the same as the value of the function at AB. If those two things are true, then we say the function is continuous at the point AB. Okay. So far this seems kind of backwards because we said continuity would help us prove that the limit exists. But here we're saying in order for a function to be continuous, we have to know the limit exists. Well, we're gonna kind of cheat. And I'm basically gonna give you a bunch of functions that are continuous you'll just have to take my word on it, basically. But once you know that a function is continuous at a point, then you know the limit exists. And this gives a really easy way to evaluate the limit. We know if it's continuous at a point, the limit exists, and it's just equal to the value of the function at that point. So then the limit has to be just whatever the value of the function is at that point we're taking the limit, if we know it's continuous. So basically we're gonna tell you which functions are continuous, and then this is how we're gonna evaluate those limits. Okay, so okay, so does it have to be continuous for? Yes. So that's one thing I wanted to mention. Continuing this definition. So this is the definition for continuity at a point. If we just say a function is continuous, that means it's continuous everywhere in its domain. So a function is said to be continuous if I don't specify a point. If I just say it's continuous, then that means if it is continuous at every point in its domain. Does that answer your question? Okay. So we're going to look at a bunch of functions which are continuous everywhere in their domain. One thing to be careful of, though, is that all the functions we're going to look at, they are continuous, but obviously they can't be continuous where they're not defined, and that'll come into play in a second. So if a point's not in the domain, we can't say anything about the limit, even if the function is continuous. Okay, so now I'm basically just going to give you a big list of functions which are continuous. So here are a bunch of continuous functions. So number one, the simplest are just going to be polynomials in two variables. So polynomials are the first kind of continuous functions. So polynomials in two variables are just like polynomials in one variable, except each term can involve both x and y. So it's going to be, every term is going to be x to some power times y times some power. So for example, if I gave you like 3x to the 4 minus 2xy cubed plus x squared y squared minus 2y. So this is a polynomial. Each term here is just some x raised to some integer power, positive integer power, times y raised to some positive integer power. That's a polynomial in two variables. All of these are continuous, which means everywhere in their domain, they're continuous at that point. And what's the domain of a polynomial? What points x, y, and y love? Oh, well, not close. So for functions of two variables, we're not plugging in real numbers. we're plugging in ordered pairs of real numbers. So all points in R2. So the domain is all of R2 for polynomials. So these are continuous literally everywhere. So if I give you a polynomial and tell you to take a limit, you know no matter what point I give you, it's going to be continuous at that point because it's defined at that point. And so to take the limit, you just plug in that point into here to get your limit. And we'll do some more examples of that in a second. So building on that, so we know polynomials are continuous. Also, rational functions are continuous. So a rational function is just basically a function where the numerator and denominator are both polynomials. So it's just a function it's just a polynomial divided by a polynomial is a rational function. So it's p of xy divided by q of xy, where p and q are both polynomials. Okay, so for example, we've already seen this example. So we have x squared minus y squared over x squared plus y squared. That's an example of a rational function. The numerator, x squared minus y squared, is a polynomial. The denominator, x squared plus y squared, is a polynomial. This is a rational function. Okay, so first problem you might have noticed is I said, I'm giving you a list of continuous functions, and I said the limits always exist for these nice continuous functions. But we did an example, the very first example we did was showing that the limit as we approach 0, 0 of this function does not exist, but I'm telling you it's continuous. What's the problem with taking the limit as we approach 0, 0 of this function? Exactly. So I said these are continuous, which means the limit exists for points in the domain, but 0, 0 is not in the domain. In fact, it's the only point not in the domain. So remember, when I say it's continuous, I mean it's only mean it's continuous for points in its domain. So for this guy, we're not continuous at the point 0, 0 because it's not defined at 0, 0. So rational functions are continuous. Let me put it this way. Rational functions are continuous everywhere except where the denominator is 0. Those are the only problem points. So these are continuous where the denominator, q, is not equal to 0. Exactly. Okay. And then finally, sort of building on those two examples, we have compositions of continuous functions. So if f is a continuous function of one variable, and g is a continuous function of two variables. So continuous function of two variables. Then f of g is a continuous function of two variables. So this might seem kind of weird, but it's really obvious once you see an example what I'm talking about. So for example, I'll use t just so we don't get it mixed up with x and y. Suppose f is, say, e to the t. That's a continuous function of one variable, we know. And let's suppose g of xy is x squared plus xy cubed. It's a polynomial, so it's continuous. So then, f of g is going to be e, but instead of e to the t, it's going to be e to the x squared plus xy cubed. So e to the power x squared plus xy cubed. So this is a composition of a continuous function one variable and a continuous function of two variables. So this guy is continuous. Once again, everywhere it's defined, but it turns out this is defined everywhere, so that's not a problem. We won't run into these that often when we're talking about limits, but that's a big other class of continuous functions. Okay, any questions so far? Even on the exam, I mean, I can't guarantee you won't run into something like this, but it'll be easy to recognize and deal with. You'll give us the answers to the final. I don't know what the final is yet, so I can't help you there. But yeah, I mean, you'll do some examples, and it won't be. They're easy to deal with, to be honest. Okay. So here's a whole reason we're talking about continuity. So suppose we have the function so let's use that x squared minus y squared over x squared plus y squared again. Okay, it's a rational function, so it's continuous as long as the denominator is not 0. So it's continuous everywhere except for the point 0, 0, in other words. So let's use that fact to evaluate the limit or show it doesn't exist. Sorry. So let's take the limit as we approach the point 1, 2 of this function. So if you're given this on an exam, you're asked to evaluate this limit if it exists. The first thing you want to check is my function continuous at that point? So is our rational function here continuous at the point 1, 2? Yes, it's a rational function, so it's continuous everywhere it's defined, and it's defined at 1, 2 because the denominator is not 0 there. So since it's continuous, by definition, the limit as we approach 1, 2 has to be the value of the function at 1, 2. So the limit is just going to be f evaluated at 1, 2. So in other words, go to your function, plug in x equals 1, y equals 2. And what do we get? negative 3 over 5, right? So we get 1 squared minus 2 squared, so 1 minus 4, which is negative 3, divided by 1 squared plus 2 squared, which is 5. And so our limit is negative 3 over 5. So if you know a function is continuous at a point, evaluating the limit, incredibly easy. Just plug in the points. Does that make sense? Will you need to write out your reasoning? No, if you, honestly, on an exam, if you just give the right answer, generally, when I'm personally grading, I'm not going to look at all the work if you give the right answer. And it's not something you could just kind of pull out of thin air. I'm not going to bother looking at the work, but it is always good just to say, you don't need to write down it's continuous at the point 1, 2, therefore blah, blah, blah. If you just write f of 1, 2 is negative 3 over 5, you should be good. That should be enough. It's understood, we know you know what's going on, so that'll be fine. Okay, so let me summarize everything we've talked about. Here, this is how you're going to approach every limit problem. So there are going to be 3 steps to doing this. So we want to know, the question is, we want to evaluate the limit as we approach a point AB of some function. So we want to evaluate if it exists, or show it doesn't exist. So here are the steps you're going to want to take for all these problems. So first thing we always want to check is the easiest thing. So does the limit exist? Well, first thing you want to ask yourself is my function continuous at AB? So is f continuous at AB? And basically for every function we're going to give you, it's going to be continuous at a point if it's defined at the point. So is it continuous at AB? If yes, then we know the limit exists. And to evaluate the limit, we just plug in AB into our function. If yes, the limit exists. And it's just the value of the function at the point AB. Exactly what we did down here. We know this function is continuous at 1, 2, so we know the limit is just the value of the function at 1, 2, which is negative 3 over 5. So that's the best case scenario. Second thing, if it's not continuous, it could still be possible that the limit exists. So if it's not continuous at that point, but if we can factor our function somehow, if it's like a rational function, and the problem is when you plug in AB, you get 0 in the denominator. If it's possible to factor top and bottom and cancel out that 0, then the limit could still exist. But we can factor and cancel the 0 in denominator. And I'll show an example of this in a second. So if you factor your function, you cancel the 0, the problem in the denominator. And if you're then left with the continuous function after you cancel, then you treat it like that function and just plug in the points. So if left with the continuous function at AB evaluate the resulting function at AB. Sorry, this is hard to read. And this will be much more clear when I do an example. So in other words, it could be possible that you're not continuous at the function at the point, but the limit can still exist. And that can happen for something like the following. Suppose our function is the square root of x plus y minus 1 over x plus y minus 1. So suppose I wanted to know the limit as we approach the point 1, 0 of our function. Is this legible? Sorry, it's... I feel like it's getting harder to read. Okay, but can everyone read this here? Okay. So first thing we want to check for a limit problem, is my function continuous at the point 1, 0? If it is, then I just plug it in and get the limit, we're done. Is my function continuous at 1, 0? What did I do? Oh, you used wrong here. Gotcha. So we're not continuous at 1, 0, why? Right, because the denominator is 0. It's not defined at that point. So we're not continuous there, so we go to step 2. Can I somehow factor this so that I can cancel stuff top and bottom, and I'm left with something which makes sense, which is continuous there. So this one, it's not immediately obvious. Well, how do we choose the points to evaluate the limit? That's simple. We just give you the points. You're never going to have to choose a point. We're always going to give you the point at which to evaluate the limit. Okay, so we have a problem. Let's see if we can do anything about it. Well, we have to be a little bit clever for this one, but notice the bottom I can factor as a difference of squares. So this is the limit as xy approaches 1, 0 of, so the top I'm going to leave as square root x plus y minus 1, but the bottom I'm going to factor as square root x plus y minus 1 times, can we read this? Square root x plus y plus 1. That's probably really hard to read. So this is square root x plus y minus 1 times square root x plus y plus 1. So notice this is just a difference of squares. This is square root x plus y squared. This is 1 squared. Does everyone agree that this is what I wrote here on the bottom? Okay, so now that we've done that, we can cancel square root x plus y minus 1 top and bottom. And when we do that, we're left with 1 over square root x plus y plus 1. Now that is a continuous function. It's a composition of functions, and it's a little complicated, but it is continuous at 1, 0 because it's defined at 1, 0. And everything we give you is going to be continuous where it's defined, basically. Does everyone see that? So when I plug in x equals 1, y equals 0, it's defined there. And so to take the limit, you just plug in 1, 0 into the new function. after we've canceled everything. So the limit is just going to be, this is why I hate this physical whiteboard. So it's 1 over square root x plus y plus 1. Evaluate that at 1, 0. We get 1 over square root 1 plus 0, which is 1 plus 1. We get the limit is 1/2. I apologize if this is really difficult to see what's going on. So does the original function just have a hole? Essentially, that's what's going on. It's like a removable discontinuity, basically. It could be a hole, it could be like a line or something, but it's going to be something similar to having a hole. And that's essentially what happens here. In fact, it's not really a hole, it's like a line where it's not defined, but we won't get into that. But it's the same sort of thing as a function of one variable where the curve just has a hole in it. Okay, so that is step 2. May not be continuous there, but we can factor it somehow. Sometimes you have to be clever. But when you factor it and cancel, you're left with something continuous at the point. Then you evaluate that at that point to get the limit. Okay. So if both of those things fail, so if steps 1 and 2 fail, if we're not continuous, if we can't cancel the discontinuity, then we're going to assume the limit does not exist. So we're going to assume the limit of our function doesn't exist, and then we're going to show it doesn't exist. And basically, for all the examples we're going to give you on an exam, the hardest thing you're going to have to check. So remember, to show a limit doesn't exist, you just have to find 2 paths where the limit along those paths is different. So the most complicated paths you're going to have to pick are just lines of slope n. So generally, we're going to tell you, we're going to look at limits as we approach 0, 0. To show they don't exist, you're going to check y equals mx. All of those are lines of slope m which go through the point 0, 0. And if for different values of m, for lines of different slope, you get different limits, then that means the limit doesn't exist. So we're going to check the lines y equals mx, showing different slopes m, give different limits. And that's how we're going to show the limit does not exist. So yesterday we did an example like where we had to, where for all of these guys, for all straight lines y equals mx, we got the same limit. But then when we checked x equals y squared, it happened to be that we got a different limit. On an exam, we're not going to expect you to come up with something clever like the x equals y squared. It will be sufficient to check y equals mx to prove that the limit does not exist. No, so you only have to evaluate the limit at the point we give you. We're always going to give you a specific point, and you only have to worry about the limit at that point. Okay. Good Lord, guys. So any questions? That's limits. What if the limit equals infinity? The limit's never going to equal infinity. The limit doesn't exist, if that's the case. Okay, so yeah. Evaluating limits, really easy. If it's continuous, plug in the point. If you can factor out the discontinuity and are left with something continuous, do that, factor it out, cancel, then plug in the point. If it's neither, we're going to assume it's the limit doesn't exist, and you're going to check along the paths y equals mx, and use that to show you get different limits for lines of different slope. Yeah. Okay. So really, the only thing you need to know how to do, the new thing you need to know how to do, is how to check limits along a path. And we covered that yesterday. And I am, wow, running way behind where I wanted to. But I'm going to go ahead and start the next section, partial derivatives. But any other questions about limits? Okay. So I'm definitely behind where I wanted to be, but that's okay. This always happens like right at the beginning of the semester or right after the first exam. And then by the time we get to the exam or whatever, we always have a ton of time left. So we'll catch up. And plus also, now we're not gonna have to waste class time on quizzes. I think I'm just gonna do those on Canvas. And you guys will have, you guys will just be able to take the quizzes whenever in a certain time frame, and it'll just probably be multiple choice, I'm thinking. Haven't 100% decided, but I think that's how it's gonna work. But anyways, we should be fine. Okay, so partial derivatives. Okay. And I'm probably just going to, if I need to, I'm probably just going to go on to until like 10 o'clock or 10:05. If you have to go, that's fine. Then you can just watch the recording later. By the way, I forgot to send out an email, but I put up the recording of the first lecture on YouTube, on the course YouTube, the link of which is on the Canvas homepage. Everyone see that? Go ahead and subscribe to that, which will make seeing the videos easier. Yeah. But yeah, I'll probably just go until 10 o'clock, 10:05 if I need to. If you have to go, then you can just watch the recording later, but yeah. Yes, be sure to like and subscribe, please. Okay. All right. So partial derivatives. Okay, so let's recall how derivatives work for functions of one variable. So for functions of one variable, suppose you have a function one variable f of x. So when you get your exams back, will you see the exam or just the score? So all the exams have been scanned. I'm going to tally up the scores. I'm going to put those scores on Canvas, and then I'm going to email you a scan of your exam. So you will see your actual exam with the grade and any corrections or anything that were put on there. Yeah. So you'll get your actual exam back. Okay. So for functions of one variable, f of x, what does the derivative mean? Okay. So if we have a function, f of x, then remember, if we look at a point A and we look at the derivative is the rate of change of our function f with respect to x at the point x equals a. So basically, that's what you always hear, but what that means is if I'm at the point A, so if you're at x equals a, and you change the value of x by a tiny bit, so you're at a and you move a little bit. So you're at a and you move a small amount. So you just change your value of x slightly. What happens to the function? So I'm at a, I change just a little bit. How does the value of my function change? The derivative tells you approximately how much it changes. So the derivative gives an approximate answer to this. Is this still legible? Okay. I feel like this is fading now. Okay. So the definition of the derivative of a function of one variable at a is really just the limit as h approaches 0 of f of a plus h minus f of a divided by h. So if you take out the limit, basically it just means how is my function changing as I move to a plus h. So if I move a tiny bit by h, so how's my function changing divided by how is my x value changing? So change in f over change in x. The rate of change of f with respect to x. So for functions of one variable, the derivative is related to how your function changes when you change your x value by a tiny bit. So for functions of two variables, we have something similar, but now instead of just having an x to change, you have an x and a y value to change by a little bit. So if you have a function of two variables, now instead of just having one number we can change, we have two numbers we can change by a slight bit. So for example, the book uses this, and I think it's a really good example. We have heat index. So heat index is a function of two variables. It's a function of the current temperature and the relative humidity. So we'll call the heat index the function I, and it's a function of temperature and humidity. Okay, so suppose we're at a given temperature and humidity. So we know the current temperature, we know the current humidity. Then the heat index, we know the heat index. It's just going to be whatever this is at T naught and H naught. So we know the heat index right now. Suppose we want to know what happens if we just change either the temperature or the humidity by a tiny bit. What happens to the heat index? So suppose we keep let's say the temperature so we keep the temperature steady, but we change the humidity just a tiny bit. So we let the temperature vary and let humidity, or so we keep the temperature fixed and let humidity vary a bit. What's going to happen to the heat index? How is the heat index changing? Well, that is going to be answered by what's called a partial derivative. So if we're just letting, fixing the temperature, letting just the humidity vary by a bit, the rate of change there of the heat index with respect to humidity is going to be the partial derivative of the heat index with respect to humidity. So the rate of change of the heat index with respect to humidity is going to be the partial derivative of the heat index with respect to humidity, and we write it as follows. Sorry, let me. At that temperature and humidity, that's going to be, we'll get, that's fine. We'll get to that in a second. I'll just give you the definition of it for now. Yeah. Is it sort of clear what I'm doing here? Okay. So I'll just give you the definition, and I guess we'll end it today there. So if you have a function f of two variables, the partial derivative of f with respect to, so let me say f is a function of two variables. So given a function of two variables, the partial of f with respect to x at the point AB is going to be the limit as h goes to 0. So the partial with respect to x, the rate of change of f with respect to x, we're letting y be constant at b, and we're changing x by a tiny bit. So f of a plus h, b minus f of ab divided by h. So this is an h here. So we're changing the x value by a tiny bit, leaving y fixed. This is how does my function change over how is the x value changing? That's a partial of f with respect to x. And another way of writing that is df dx, but notice I'm not using a normal d, I'm using a fancy squiggly d. So at the point AB. So when I use a squiggly d, instead of a normal d, that implies that it's a function of two variables. This means I'm taking a partial derivative, not a regular derivative. So I can take the partial of a function of two variables with respect to x, and I can also take a partial with respect to y. F sub y at the point AB is the same thing, except now I'm leaving x fixed, changing y by a bit, and then doing the same thing. So that's the limit as h approaches 0 of f of a b plus h minus f of ab over h. And similarly, instead of writing f sub y, which is one way to write the partial, I could just write df dy using squiggly d's. And if I want to specify that at the point AB, then I just write at AB. Okay, so these probably mean nothing to you. That's okay. As we saw from 140 and 141, taking these limits generally kind of sucks. But it'll turn out, as we'll see next time, you don't need to learn anything new. You already know how to take partial derivatives. And there's a very simple rule for that. But we'll talk about that next time. So any questions before I hang it up? Okay, all right. Thanks for coming to lecture and bearing with me during the quarantine. Hope everyone has a nice weekend, and I will see you guys next week. And I'm sure I'll have a number of announcements. I'll send out emails. I'll try to get everything graded today and have your exam sent to you, and et cetera, et cetera. Yep, you guys have a good day too. And see you guys later. Are you getting homework today? Yes, I will assign some homework today. It's just going to be by paper, because I'm not sure. I still haven't heard back about the free textbook thing. I'm gonna have to talk to some people about that, but still not sure about that, unfortunately. But yes, there will be homework that I'm gonna assign today and will be due next week. Will there be a corona curve? So if there's a corona curve, it'll be a pass-fail situation in this class, and I'm not sure whether that's going to be the course policy yet. It depends on what the course coordinator says, but that's a possibility. But yeah, is tablet PDF handwritten? Okay, absolutely. However you want to turn it in. If you can turn in something legible that you can upload the file of, then that's fine. Be it a PDF or just a picture of your handwritten homework. That's fine too. Oh, okay. So generally, there's usually at least a small curve every semester on the syllabus. There's a grade breakdown, so there's cutoffs for A minus, B minus, etc. Generally, those are adjusted by a little bit at the end of the semester, and those take into account the grades on the exams. We don't know how that's going to go. Every semester I've done this, there's been at least a small curve, but that's just unrelated to the current pandemic situation. Can we still see your dog? If I can get him in here. I have two dogs actually. So here's one of them. This is, can we see him? Yeah. This one's Atlas. He's lazy. And this one's Kirby. He's a crazy one. And who knows, maybe you guys will see more of them next semester or later on. Anything else?
So see you guys later. Have a good weekend. Stay safe. Thank you.